Physics from Moscow Institute of Physics and Technology MIPT and Vladimir State University, Russia have achieved a nearly 90% efficiency converting light energy into surface waves on graphene. They relied on a laser-like energy conversion scheme and collective resonances. Their research paper came out in the journal Laser and Photonics Reviews. Manipulating light at the nanoscale is a task crucial for being able to create ultra-compact devices for optical energy conversion and storage. To localize light on such a small scale, researchers convert optical radiation into so-called surface plasmon-polaritons. These SPPs are oscillations propagating along the interface between two materials with drastically different refractive indices, specifically a metal and a dielectric or air. Depending on the materials chosen, the degree of surface wave localization varies. It is the strongest for light localized on a material only one atomic layer thick, because such 2D materials have high refractive indices. The existing schemes for converting light to SPPs on 2D surfaces have an efficiency of no more than 10%. It is possible to improve that figure by using intermediary signal converters, nano-objects of various chemical compositions and geometries. The intermediary converters used in the recent study in Laser and Photonics Reviews are semiconductor quantum dots with a size of 5 to 100 nanometers and a composition similar to that of the solid semiconductor they are manufactured from. That said, the optical properties of a quantum dot vary considerably with its size. So, by changing its dimensions, researchers can tune it to the optical wavelength of interest. If an assembly of variously sized quantum dots is illuminated with natural light, each dot will respond to a particular wavelength. Quantum dots come in various shapes: cylinders, pyramids, spheres, etc., and chemical compositions. In its study, the team of Russian researchers used ellipsoid-shaped quantum dots 40 nanometers in diameter. The dots served as scatterers positioned above the surface of graphene, which was illuminated with infrared light at a wavelength of 1.55 micrometers. A dielectric buffer several nanometers thick separated the graphene sheet from the quantum dots. The idea to use a quantum dot as a scatterer is not new. Some of the previous graphene studies used a similar arrangement, with the dots positioned above the 2D sheet and interacting both with light and with surface electromagnetic waves at a common wavelength shared by the two processors. This was made possible by choosing a quantum dot size that was exactly right. While such a system is fairly easy to tune to a resonance, it is susceptible to luminescence quenching, the conversion of incident light energy into heat, as well as reverse light scattering. As a result, the efficiency of SPP generation did not exceed 10%. The essence of the hybrid interaction scheme is that rather than using just two energy levels, the upper and lower ones, the setup also includes an intermediate level. That is, the team used an energetic structure akin to that of the laser. The intermediate energy level serves to enable the strong connection between the quantum dot and the surface electromagnetic wave. The quantum dot undergoes excitation at the wavelength of the laser illuminating it, whereas surface waves are generated at the wavelength determined by the SPP quantum dot resonance. The researchers have worked with a range of materials for manufacturing quantum dots, as well as with various types of graphene. Apart from pure graphene, there is also what is called doped graphene, which incorporates elements from the neighboring groups in the periodic table. Depending on the kind of doping, the chemical potential of graphene varies. The researchers optimized the parameters of the quantum dot, its chemistry, geometry, as well as the type of graphene so as to maximize the efficiency of light energy conversion into surface plasmon-polaritons. Eventually, they settled on doped graphene and indium antimonide as the quantum dot material. Despite the highly efficient energy input into graphene via the quantum dot intermediary, the intensity of the resulting waves is extremely low. Therefore, large numbers of dots have to be used in a specific arrangement above the graphene layer. The researchers had to find precisely the right geometry, the perfect distance between the dots to ensure signal amplification due to the phasing of the near fields of each dot. In their study, the team reports discovering such a geometry and measuring a signal in graphene that was orders of magnitude more powerful than of randomly arranged quantum dots. For their subsequent calculations, the physicists employed self-developed software models. The calculated conversion efficiency of the newly proposed scheme is as high as 90% to 95%. Even accounting for all the potential negative factors that might affect this figure of merit, it will remain above 50%, several times higher than any other competing system. A large part of such research focuses on creating ultra-compact devices that would be capable of converting light energy into surface plasmon-polaritons with a high efficiency and on a very small scale in space, thereby recording light energy into some structure.